Hello everyone, my name is Richard Marshall and I'm from the Australian Bureau of Meteorology. In this presentation we'll cover an application developed for the Australian power industry to provide situational awareness of the impacts of space weather on the power network. Geomagnetically induced currents, or GICs, caused by space weather can impact critical infrastructure such as power networks and resource pipelines. The Bureau of Meteorology's Space Weather Services has developed models that provide estimates of GICs flowing throughout the network via an API in near real time to the control room environment. This work has been done in collaboration with industry, academia and other Australian government organisations such as Geoscience Australia. Before describing this work in more detail, I'll just provide a quick overview of the Bureau's Space Weather Services. The Bureau's Space Weather Services was formerly the Ionospheric Prediction Service, providing HF radio communications advice since the 1940s. In the 1990s, IPS broadened its scope to include additional space weather advice and underwent a name change. In 2007, the former IPS joined the Bureau of Meteorology, and in 2014, we officially became Space Weather Services under the Bureau's realignment project. Space Weather Services provides a range of reports, warnings and forecasts on the general space weather environment. However, we also provide more specific products and services for a range of critical infrastructure, such as satellites, GPS positioning and timing, aviation, defence, energy and resources, and the power industry, and that will be the focus of this presentation. The GIC application described in this presentation comprises a number of separate elements. There is the geoelectric field model, which requires knowledge of the spatial and temporal variations of the geomagnetic field, together with the Earth impedance functions, which are derived from a number of different Earth conductivity models, such as a uniform half space, a 1D n-layer model, and a 3D conductivity model. The network model requires an electrical parameter model for the transmission line branches, models of the transformer electrical connections and configurations, and a network analysis or GIC model. The application also considers the user requirements, such as the output being validated with measurements from within the network, and the model output being available in a user-friendly format for application in a control room environment. As mentioned previously, for this application, we need knowledge of the geoelectric field, and this can be obtained through this fairly general expression here, which has an impedance tensor as well as information about the spatial and temporal variations of the Earth's magnetic field. For a conductivity structure that varies vertically or in one dimension, the expression simplifies to just use the off-diagonal elements. The spatial and temporal variations of the geomagnetic field are derived from a network of geomagnetic field monitoring sites across Australia, indicated by the red triangles in the figure, overlaid on the geology of the Australian region. The complex geology requires analysis of various conductivity models. So for this application, we used a number of different Earth conductivity models to derive the impedance functions. So we used a uniform half space, as well as an n-layered 1D model, as well as three-dimensional conductivity models to derive modelled magnetotelluric or MT impedance tensors, which I'll discuss in a minute. For the uniform half space, essentially we have an incident plane wave and we parameterise free space and the Earth. And to obtain the geoelectric field, we have a fairly simple formula for the impedance. For a layered 1D model, again we have an incident plane wave and parameterised free space and the Earth conductivity via a number of different layers, and the complications in the expression arise due to the reflections at the boundary interfaces. And to obtain the geoelectric field, we therefore use a recursive expression. It's more complicated, of course, than the uniform half space, but it's been used by a number of authors previously. For conductivity varying vertically and horizontally, modelled MT impedance tensors have been derived from the 3D 21-layer conductivity model of the Australian region shown in this figure. The modelled MT impedance tensors were computed using this 3D conductivity model and the MOD-EM 3D algorithm of Egbert and Kelbert, and have been validated with measured MT tensors obtained from the Australian Lithospheric Architecture Magnetotelluric Project, or AUSLAM. This work has been conducted by Geoscience Australia. The validation compared measured and modelled tensors at locations across Victoria that represents the range of different underlying geology for this region, coastal, inland and a fold belt location, where the near surface sedimentary and igneous rocks were subjected to folding, faulting and uplift. For each of these locations, the tensors from 3 AUSLAM sites were compared with the modelled MT tensors for the same sites. Apart from a static shift distortion effect in the amplitude of the measured tensor for one site, the model tensors generally showed good agreement with the measured tensors at frequencies less than 10 MHz. So all the different approaches to derive the impedance functions using different conductivity models that we've just been describing produce different geoelectric field patterns across our region. For example, the uniform conductivity model, the one-dimensional n-layer conductivity model where each layer is uniform across that layer, for a one-dimensional n-layered conductivity model where the conductivity varies from within a layer, and then there are the impedance functions derived from a 3D conductivity model. And you can see there's considerable variation between these different geoelectric field patterns over our region, and all these will be tested during the validation process of this application. So the Australian Power Network extends from Queensland in the north to Tasmania in the south, and then across into South Australia. It's thousands of kilometres, and there are multiple operating voltages. There's over 2,000 nodes or buses in the system. There's over 1,500 branches and over 1,000 high voltage transformers. To model it, we use a linear approximation to this network. And we also have to include the electrical parameters that are within the network. So we use a single phase pi model to model the transmission lines. However, these are 3-phase, so we need to consider that as well in the model. We also need to consider that the transmission lines then connect to buses, which then connect onto the transformers. And we also then need to consider that the transmission lines then connect to often multiple transformers in a transformer bank. We also need to consider the transformer winding configuration. So here we have the models that we use for a transformer star winding configuration or a transformer auto configuration, and we also include delta star and star delta winding configurations in this model. To do the network analysis, there are a couple of methods that are typically used: the nodal admittance matrix method or the mesh impedance matrix method. So for this application, we're using a network admittance matrix and the formulation of Lettinen and Piola, and the geoelectric field that we've been talking about makes its way into the formulation down here. And if we solve this matrix equation, we can find the currents or the GIC flowing throughout all nodes within the network at a particular instant in time. If we run this over the course of a storm, we can generate time series with which we can then compare with observations from within the power system itself as part of the validation process. So for validation, we use observations that are taken from the transformer neutrals at various locations within the power system. So the observing equipment looks like this. It's located at a number of locations, and we can use those time series to validate the various approaches in the modelling technique for this application. So as part of that validation process, we'll be comparing here the measured and modelled GICs. Here we have the measured GIC on a transformer neutral in the north of the country. The red is the model output using a uniform conducting half space model. And as we go to 1D models and then eventually the impedance functions derived from the 3D conductivity model, the agreement tends to improve. So as another example, this time in the very south of the country, Down in Tasmania, again, we have the black trace is the transformer neutral, the red trace is the model output from using the uniform half space model, and again using 1D conductivity models of increasing complexity through to the modeled MT impedance tensors from the 3D conductivity models. You can see again the comparisons are really quite good. Not all stations compare as well as these. However, generally speaking, there tends to be pretty good agreement, and this gives us confidence in the model and confidence in using the modeled MT impedance tensors as part of this application. So as well as validation, implementation also needs to be considered. The application needs to be user-friendly, needs to be able to be implemented such that it can be used for a control room environment. So the output of the model is through an API. The power company software can send a JSON request and receive a response from the API. The API on one side of the firewall includes the conductivity models, the magnetometer data, and the network parameters, as well as a database that includes the authentication key for the API for a security reason. And then when the power companies receive the response, it was delivered in near real time so that it can be used in a control room environment to provide situational awareness of space weather impacts on the power system in near real time. So just an example of how the API may look. Again, this is back to our southern state and our most northern state of Queensland and our southern state of Tasmania on the right. And this is just for a very modest storm back in 2013, I believe it is. It's an example that we have, but this is how the output in the control room may look, or example of how it may be used. So in summary, a GIS application has been developed in collaboration with industry that models the impacts of space weather on the power system. The models and the application have been validated with end user data. The usability of the application has been considered throughout the process such that it provides model output to the control room environment in near real time to provide situational awareness during space weather events. And future work would look to upgrade this application to utilise the outputs from global magnetosphere models such that we have a improved lead time for the model output. And I'll close by just saying thank you for watching.